Thank you. Hello, everyone, and thank you so much for joining my session, Build and Deploy PyTorch Models with Azure Machine Learning. My name is Henk Boelman, and I'm a Senior Cloud Advocate at Microsoft. I'm based in the Netherlands, but today I'm broadcasting from London. So what are we going to do? We're going to talk about machine learning on Azure, and we're going to build a Simpsons classification project using Azure Machine Learning and PyTorch. So first, let's have a look what machine learning on Azure actually entitled, like services are out there. So if you look at the top of the stack, there are our sophisticated pre-trained models. These are models that we at Microsoft train and expose to you through an API. So the only thing you have to do to get vision, speech, language, or anything in your project, you just have to send data to a REST API endpoint, and we will give you the results back. And we take care of all the infrastructure under that. If you want to train your own models, you need a framework. And the good thing is Azure Machine Learning supports all the frameworks out there, like PyTorch, TensorFlow, Keras, Onyx. So you can choose your own framework, and today we'll obviously go for PyTorch. Then there are productivity services, some services that help you kind of do your work faster. So there's Azure Databricks, Azure Machine Learning, and then machine learning virtual machines. And these machine learning virtual machines are really cool if you want to have a quick start in setting up your environment, because we all know that it takes like a lot of time to get Python right, to get your GPU drivers installed on your local machine, and then keep that working for all your other products. So you can just spin up the machine, all the frameworks are installed, GPU drivers installed, so you can start within 10 minutes with your machine learning project. Then we have a lot of powerful infrastructure in the cloud. We have a lot of CPUs and GPUs that will actually help accelerate your training. And when your model is done, we can give you the model, of course, so you can run it on-prem. Then we can help you deploy it in the cloud, and we can even deploy it on the edge for you using IoT Edge. So, cognitive services. I already touched a little bit about them, but they are pre-trained models in the cloud and on the edge, meaning that you can create an endpoint in Azure and you can send your data through that. But for some scenarios, you kind of don't want to do that and want to run them locally on your devices. So some of these cognitive services, you can actually get as a container, and you can deploy in your own infrastructure so that the data will just not leave your own network. The only thing that it needs is like internet connectivity, so it can send back the billing information every 15 minutes to Azure. So that is really great, and you can scale it, and you can run them as large and on scale as you want. So these cognitive services are divided in 4 regions. So there is vision, speech, language, and knowledge. So there is vision to make your application see. There is speech to make your application listen and talk to you, and talk back to you. There is language to understand what is being spoken. And there is knowledge if you want to tap into the big of the brain of the internet. But today we're not going to talk about cognitive services. We're going to build our own. So we're going to level up. And for that, we're going to use Azure Machine Learning Studio. Azure Machine Learning Studio is a fully managed service that enables us to do the whole process and do that together, from training our data to actually running our models in production. So it covers the whole spectrum of an AI lifecycle. And that is great. And today we're going to use my Simpsons dataset to answer the question, is it Marge, Homer, Bart, or Lisa? We can have this dataset on my GitHub, github.com/henky/dataset-lego-figures. They consist of 10 images or 10 figures, 10 different Simpsons characters, and every character has around 50 images. So our dataset is not that large. So what are we going to use to actually train that model? We're going to use Azure Machine Learning, obviously. We're going to use the PyTorch framework. We're going to use the GPU cluster, and then we're going to deploy it to the cloud. So how would a process kind of looks like if we want to do that? So we have a data scientist that is going to craft the model for us in Jupyter notebooks, in his or her favorite tools. Store it to version control, then use Azure Machine Learning to train it on scale, and deliver the model in a service called model management. Then a developer can pick that model up, write software around it, put that software in version control, set up a build pipeline, and probably it will end up in an Azure Container Registry. And then operations can pick that container up and deploy it like they would deploy any other container. And then our client can send images to the endpoint running an Azure Kubernetes service in this case. So what is Azure Machine Learning? So it is not just one thing. It is a set of Azure Cloud Services that can be controlled using the Python SDK and the Azure CLI. And that set of cloud services enables us to prepare our data, to train models, to track experiments, and finally deploy our models. So to do this, we need to go through 3 stages. First, we need to start and prepare our Azure environment. Then we can start experimenting with our model and our data. And finally, we need to deploy our model so actually people can use it. So let's start with step 1. We can set up our environment in multiple ways. We can do that using the Azure portal. We can use AI tools for Visual Studio Code. We can use the Python SDK, and we can use the Azure CLI. I like to do things in code, so from now I'm just going to show you Python code. So to create a workspace, you install the Python SDK, and then you can start using the SDK and say, workspace create, give it a name, point to your subscription ID and resource group, and specify your location. The location is already an important decision you're making, because when you're training, you're going to use machines, virtual machines. And not every virtual machine is available in every region. So before you create your workspace in a specific region, check if the compute you want to use is available in that region. And with West Europe, you're always kind of good to go. So you create that workspace and then you write out a configuration file. And with that configuration file, everyone else can connect to that same workspace by saying workspace from config. And this is how it looks. ml.azure.com when you have your workspace. You see it lives outside of the Azure portal and it has its own nice, clean interface. Let's dive in some things you can actually do there. So first, we have datasets. On the datasets is where our registered dataset lives. So let's say you upload a bunch of images to a data store, in this case a blob storage. And then from that data on that blob storage device, you can create a dataset. And you can use that dataset later on in your experiments to train your model. Then there are experiments. Like we are going to create an experiment Simpsons classifier. And every time we try to train the model, a new run is being created, and all the logging and all the metrics and everything is grouped under that experiment. There are models, because we have to save the output somewhere. So when the training run is done, we have some artifacts, and we can register those artifacts in model management. And everyone else can connect to model management and pull out that model. Then there are endpoints. Here is where our deployed models live and our pipeline endpoints, where our training workflows live. There is compute. Here we manage our different types of compute. And under data stores, we actually manage the connections to where our data is. So now we know that we need compute. We need something to train our model on. So here I'm saying Azure Machine Learning Compute provision for me a cluster that consists of standard NC6 machines. These are NVIDIA machines with a GPU, and always have one node up and running. And if you're going to do something on scale, you can have a maximum of 6 nodes up and running. So this actually consumes constantly my credit card for the one machine. So it is better if you set minimum nodes is 0, because then the cluster will automatically shut down after 3 minutes. But it adds that extra time for the node to start up. Creating a cluster takes around 5 to 10 minutes. So next we need storage, because we need to have a place where our data is going to be stored on. So there is a default storage, that is a blob storage that is created when you were creating your environment, which you can connect to every other data store, blob container, and even outside of your Azure subscription. So let's take a look at Azure Machine Learning, and let's click a little bit around the workspace. So you see there are a lot of different options here. So let's start from the data store. Under data stores, we have all my different data stores. So we have Azure File Shares, we have blob storage, and here I can connect to other data stores. And that includes like an Azure Data Lake, Azure SQL database, MySQL database. So here I can manage the connections. And this is really cool because in my code, now I don't need to type any secrets. I just have to reference to a data store. From a data store, I can create a data set. So here are the Lego Simpsons data set. And here we can see what is actually in the data set. So we are at version 3 of the data set. And there are around 535 images in. It's created by me. This is when it was created. And here is the location on the workspace blob. So we can actually go there and kind of look how the directory structure looks like. But we can also explore it and kind of quickly preview the data set from here. So here we have our Simpson Bart. Probably if we scroll a little bit down, we hopefully have someone else. Here's G. Wiggum. So they're all here. Tells you also, gives you some code samples how to actually consume it. So how to connect to it, how to use it in Python code. And we can easily create a new version from it here. Under compute, we have our different types of compute. We have compute instances, compute clusters, inference clusters, and attached compute. So compute instances are there to run your Jupyter notebooks on. So these are instances and they run your notebooks. And that is what we're going to use. So here you can go to Jupyter Lab, you can connect to VS Code. These things you kind of have to stop and start manually at the moment. Here are the compute clusters, and this is the compute cluster we saw in the slides. I have 8 nodes up and running because I don't want to keep you all waiting. And my compute cluster is called Optimus Prime. So Optimus Prime has 8 nodes up and running. They're absolutely doing nothing. The only thing they're doing is billing my credit card. And here we see the type of machine that is being used. So the standard NC6 has 6 cores, 56 gigabyte of memory, and has one NVIDIA Tesla K80 GPU in it. It's dedicated, so it's only for me, and I didn't deploy it in my own virtual network. You can deploy these machines in your own virtual networks, but I didn't need it for the demo, but it is an option if you need it. Here we can see the different nodes and connect to these different nodes. Here we see what kind of runs went on, and monitoring is new, so this is pretty cool. So here we actually see how our nodes are doing and how much energy is being used. It's pretty cool. GPU usage, well, that is nice. Then there are inference clusters. Here you can create like an Azure Kubernetes service and all the other type of things you want, and here you can attach to like other machine learning platforms. I actually never done that. I have to start playing with that once. So that is compute. You see here I have 2 types of compute depending on my machine learning workload. We have Bumblebee, that is just CPU enabled machines, and this one has GPU enabled machines. Here we have experiments where we can see all the different experiments I've done, models, where all my registered models are, and endpoints where my models are actually deployed. So I will go to, you can go to notebooks, but you can also use the Jupyter version. There are built in Jupyter notebooks in Azure Machine Learning, but I still prefer to have a Jupyter notebook. So this is the notebook we're going to use during this presentation, and it is also available on my GitHub. So we'll run this cell, and here you see I'm using the Azure ML SDK version 1.28. It's a bit older, but it still works. So let's start and set up our Azure Machine Learning workspace. So I'm connecting to my workspace because it already exists by saying workspace from config. Then connect to my compute target. That one is called Optimus Prime. So I just say compute target, workspace, Optimus Prime. Connect to my default data store, because here I'm wanting to store my data on, my Simpsons images, and I'm going to use the experiment Simpsons PyTorch. Next, I need my data. So I'm going to download my data from my GitHub. Then I'm going to unzip the zip file, and then I'm uploading it all to my data store. And when my data is uploaded, I can create a data set from my images. So I'm going to go to data store. I'm saying the data store part, everything in Simpsons Lego V3 and all the files there, create a data set, a file data set from files on this location. And I'm registering the data set. And now I can connect to the data set. I've already done that because we all don't want to see me uploading 500 images. So now I'm connected to my data set and I can use that actually in my training. So let's do a quick preview of what is in the data set. I've already kind of seen it, but let's pick some random images from the data set. And here we see the 10 classes again. So next, we start training our model. So what have you seen here in the first step? We've created a workspace, we created compute, and now we have storage, and we're connected to our data store. So we are all ready to go to experiment with our model and data. First thing we need to do is create or connect to an existing experiment. And then we need the magic file that will actually do the training. So I will dive into that in what actually is in the training file during the demo. We need a file that takes in the data and delivers us the model. Then we need to configure how the training script has to run. So we can either pick a curated environment. These are the environments Microsoft maintains and kind of keeps up to date. So that saves you a lot of work. But you can also create your own custom environment if you need something very, very specific. So curated environment, there is just a list available. You can see all the different types. You have Azure ML, PyTorch 1.6, 7, 8, and also TensorFlow, of course. So you get that, you clone it, and you can use it. Or you pick your custom environment and you start from a base image, and then you start like, oh, I also need these pip packages installed. Oh, I'll also use Conda to install these packages. And then that environment you can save and later on also reuse. So now you have your environment, you have your training file. Now you need to configure how your job is going to run. So what you do is you create a script run configuration. Tell it where your training scripts are, which script it has to execute, on which computer it has to run, which environment it has to use, and then you can parse some additional parameters in it. In our case, we want to tell our script where the data is. Then we submit that script run configuration to our cluster. We'll pick it up, we'll start spinning up the compute, and then it will start running our code. And while it is running our code, it is actually sending back all kinds of information about what is going on. We can have like live metrics, how our accuracy is improving, or actually maybe how it is not improving, so we can stop our job. And we see all the log files real time. So let's start and do that. So you need a training script. So I went to the PyTorch website and took the script that is doing transfer learning and classification. So I picked that example file and I pasted it here. I only added a few things. I added the ability to parse incoming arguments and an argument to connect with my Azure Machine Learning. I'm connecting to the current run context here, and I'm parsing the incoming arguments. So this is where the data actually is. Then I didn't change that much. I changed one or two more things, but then the script goes on as is. Here, where the train model is, in the training loop, I added some extra logging. So I'm logging the current accuracy and the loss here. And because it is all the same name, it ends up being an array with floats. And then Azure Machine Learning automatically understands that it is numeric data and starts drawing graphs from this data in real time for you. Finally, you have to actually save the model in a folder called outputs, because this thing is running on your compute cluster. And when it is done, and you didn't copy out your artifacts are gone. So everything you put in the outputs folder is by default copied back to Azure Machine Learning and to your run in your experiment. So now we have our training script. So I'm using a curated environment, Azure Machine Learning PyTorch 1.6. And now let's configure our script run configuration. So let's kind of run it. So I'm saying, use my Simpsons dataset as a named input, name it Simpson, and mount it. So what this command does, it mounts the folder where my data is as a virtual directory in the container where my training script is running in. So my training script can use this parameter, and there it will just say /mount/Simpson/ and then my file structure. So the training script doesn't even know that it is a dataset somewhere very stored, that it is just a directory. Then I specify the number of training rounds, where the training script is with our compute target, Optimus Prime, our environment, we create it here, and the incoming arguments. I submit it, and then I can use this widget, run details from this run, to actually visualize what is going on. So here we see from the 8 machines that are up, 1 is now actually doing something, and the current state is job is in a scheduled state. And is that actually true? Yeah, that is true. But it is already showing metrics. So that's cool. So it is running. It should be done in like 2 minutes. And that run.log function in my script made sure that these graphs are actually happening and that we can follow real time what is going on. So let this job do its work, and let's see what is actually going on under the hood. So we are in my Jupyter notebook, and when I hit submit experiment, a snapshot was made from my folder where my training script and other scripts are in, and copied over to my experiment. Then a Docker file is being created according to my environment specifications. And that Docker environment, the Docker container, is being deployed to our compute cluster. Our data stores been mounted. A training script has been launched. And while the training script was running, it sent all the metrics back to the experiment. And then because I had that widget, I can actually connect to the experiment and see what was going on. And finally, it copies over everything in the output folder and stores that in the experiment. So now the model should be done running. So I will tell you now what we have to do. We have to register the model when it is done. So here we say run, register our model. We call it Simpsons AI, and you can find the artifacts in the outputs directory. So let's see if our model is done. Yes, the status is completed. Here we should see some more log files. but I will show you them here in Azure Machine Learning. We can go to experiments. Okay, go to Simpsons PyTorch. Zooming out a little bit. This is our latest run, 12:21. That is actually my time, so that's good. Here I can click. So we went metrics, images, data, outputs, and logs. So this is okay. So this is the log that has been generated by my training script. You can find it back here. And here in the outputs, we can actually find the model back that I've been saved. And here is the labels file with all the different classes we have. Under snapshot, you find back your training script and everything that was in the training folder. So like here is the training script. Under logs, you can find way more logging files, like how your cluster is doing, all the things you need to debug if it is not going the way you want it. The metrics are stored here, so we can actually see the training accuracy, how it went. We can have that in a table, so here we will see the actual values. So, and these later on we can compare to other runs to pick the best parameters for our model. Let's now actually register our model. So we're going to register our model. We call it Simpsons PyTorch. Tell it can find the artifacts in the outputs folder. It's made with PyTorch version 1.6. Can give it a description, and I will tag it with this conference. And here I will tell it, if you're going to run this model, you probably want to have at least one CPU and 2 gigabytes of memory. So that later on, when you deploy your model, you can actually use that configuration. It's totally optional to do that. So now the model is registered, version 78. And you can go to models and actually find version 78 here. So we see it has been tagged, format was custom. But the cool thing now, what makes Azure Machine Learning like really cool is, we can go from our model back to the experiment. In the experiment, we can find back the data. So now we can trace this whole process. So if someone asks, what data is being used, you can just say, what logging was generated? What was your accuracy? How did the model train? Everything is there and available and traceable for everyone. So that is one thing that I think is super cool. So let's download our model and give it a spin. I have a set of pen testing images, and what it now will do is it will load our model in, load the labels, and then it will use this scoring function. So it will process all the data to the same tensor as the training image. Then it will run that through the model, and then it will return the result. And this final thing will just put the images nicely so we can actually see it. So here they are. And let's see, Milos, March, Homer. Okay. Didn't recognize Homer, but it didn't train for that long. We have Krusty. It's doing well on Krusty. And we have Lisa, and we have Nat here. So for 1 minute of trading, it is actually fair. So we have our model sitting in model management. So now it is time to move on and actually deploy it. But what have we done in step 2? We've created an experiment. We got a training file. We configured how this training had to happen, which training file, which environment, which parameters it had to use, and then we submitted that script run configuration to our cluster. Started running, and when it was done, we registered our model. So now it is time to actually deploy our model to an environment where other people can use it. So we can do that in a few different ways, but it all starts here. First, we need our model. We need a script that can actually make sense of the model, loads in the model, does the transform of the incoming data, and return the result. And we need a file that specifies how this environment has to look. Wrap those three together, and we get another Docker container. So let's look at how the script has to look. So first you have an init method, and you have a run method. The init method loads the model. It does that once, because loading in models takes time. And then we have a run method, and that one is initiated every time an API request comes in. It takes the URL, shapes the data, and then predicts the on the incoming data, and then returns the result. The environment file is a conda environment file, where you just specify which packages you have to use. Then there's an inference config that's kind of combines what runtime it has to use, which script entry script, scoring script it has to use, and which environment file. And with that inference config, you can start deploying it. So now we just need to specify how we have to deploy it and how that environment has to look. So we have the inference config, and now we're going to need a deployment configuration. So we can deploy on multiple ways. We can deploy to an Azure container instance.
Henk?
Yes.
Maybe a question here for the audience to know. What does it mean, inference?
Oh, inference is actually that you run data through your model. Yeah, it's rather a fancy word for just, if you see your model as a function, data in, result out. If it is a model, they call it inference.
Okay, thanks.
Yeah. So we can deploy to multiple types of environments. We have an Azure Container Instance. That is the easiest way of doing. We have linked Azure Kubernetes services. And since a few months, we have Azure Managed Endpoints, which are really cool. But we will choose the easiest thing and deploy it to an Azure Container Instance, because the other deployment can take quite some time. So this is the kind of fastest and easiest way to see if your container is running. So we have our Azure Container Instance deployment configuration. How many CPU cores, how many memory? Then we say model deploy it using this inference configuration and deployment configuration, the model, and we give it a name. So AKS, you just need to connect to your Azure Container Instance before. So let's take a look and actually see if we can get our model up and running. So here we have our deployment script. We load in the model. We load in the model and the labels in the outputs folder. So we're loading it. We're loading the labels. So this is hit once. And then on every request, this model, method is being hit. And we expect JSON data. We save it. Then we do some transformations. Then we check if it is running on a GPU or CPU enabled device, and then we score. So we run the transform data through the model, and we get the result, and we return the label and the probability, and then we remove the temporary file. So let's write that. So we have our scoring script, and now we can create an environment file. The only thing what I always like is I want to have full control over what is running in production. So I start with a clean environment, and I will call it Simpsons Inference, adding only the packages I need, and that will deliver us this configuration. So now I have my scoring script and my environment. I can tell it how the inference has to do. So we create an inference config. So this inference config can go to all the different types. So now we're going to deploy it on an Azure Container Instance. So we need to connect to our model. also version 78, that was our model. And here we create a new deployment configuration, and we see we get this parameters, how many CPU cores and how many memory, from our model, because when I registered, I set a preferred configuration, but I can easily just overrule it here. So let's create a configuration and then actually start deploying it. So here I say model deploy. This is my workspace. This is the name of deployment or my Azure container instance. This is the model you have to use. This is how you have to run the model. This is how the deployment, how the configuration, how the environment has to look. And if it already exists, just update it with a new version. And then here we say wait for deployment and show the output. So the model has already deployed within half a minute. That is extremely fast. So now our container is running in an Azure container instance with our model and with our scoring script. So we can connect to that ACI web service and then ask, hey, give us the scoring URL. So if you're starting to post images now to this URL, it will tell you which Simpson is on it. So let's do that and start testing this API. So here I have a bunch of images with all the Simpsons on it. And here is a small script that will get those images, resize them, and then runs them through the API service. So this is a really nice wrapper, so you don't have to write out the whole post comment. That will do it for you. And then the only thing you have to specify is the JSON data that you want to send to it. So URL and image, and it loops through that list of images. And then it returns, prints the results and the label on the image. What we see here, and we see that it is still not good in recognizing Mr. Burns. So we're actually talking to the same model now. So this is really cool. So what we now can do is we can just take Wiggum, go to models, and we know you could go back to where the data come from, but we can also from here see where our model lives. So this is our deployment. We can click on it. We can test it, send some data to it, hit test, and see that it now returns, hey, this is cheap, Wiggum. I think we can do it also with Bart. We can also do it with Lisa, but posting to our endpoint. We have a deployment log where we can actually see what all went on, even if it is maybe crashing. And finally, there is a lot of sample code on actually how to use this and send data to it in Python and R and C#. So that is really cool. And also from this endpoint, you can actually go back to the model, and so you can trace back which data was being used. It's the endpoint, the configuration. Actually, this is the GitHub URL. So we can also go back to version control. We didn't tag it, but you can also tag it here. So that is endpoints. So next, I want to talk to you about automated hyperparameter tuning. So what are hyperparameters? You saw I gave how many training rounds the model had to do when I was actually submitting my job. I gave incoming parameters. So machine learning models can have like a lot of parameters, and some work better than the others. So you have to tune them. So you can have a learning rate, how many layers your network has to use. And it is a lot of work to create all these different types of configuration, and especially when you have to run them all manually. So we can help you with that. So the typical manual approach would be you have your data set, you have your algorithm, you have your parameters that delivers model 1. Then you do like your second parameter, derivative model 2, 3, and so on and so on. So this is like really complex, tedious, repetitive, time-consuming, and it is expensive because you're constantly keeping track of all these parameters. So luckily, there is a better way of doing that with automated hyperparameter tuning. So what this can do for you is sample all these parameters and submit a bunch of jobs and compares the output and then gives you like, hey, these are the optimal kind of parameters for your model. And the cool thing is it can also stop if it is seeing like, oh, those parameters are going nowhere. So that will just kill the jobs for you automatically. So let's do that with our Simpsons model and see if you can get a better model out of it. So I'm going to a new notebook. This is all the same. So I'm still connecting to the same environment, same Optimus Prime, same experiment, same workspace. So Optimus Prime, Simpsons PyTorch. I'm using a slightly different data set. I added a few more Lego figures to it, which we can see here, to make it a little bit more difficult for the algorithm. Preview, please. So here we see I added like a fireman and some other Spider-Man and some other figures. And here we have almost exactly the same script. So I added just these two extra parameters, the learning rate and the momentum I made variable. And I added a log function for the final accuracy of the model. Then everything is exactly the same, except that the momentum and learning rate are also available as input parameters and not hard-coded in the script. So let's write out this training script. I'm going to use the same training environment because it is the same script. But now I'm going to specify how my hyperdrive has to run. So let's start. This is exactly the same script and configuration that we had in the previous job. But now I'm going to figure how this script run configuration has to run in the hyperdrive. So let's start here. So these are the arguments that will parse into the script. And these are the three arguments that it is going to sample for us. So here we have the number of training runs, the learning rate, and the momentum. And it's going to just pick random values between these three numbers. Then I'm specifying hyperdrive configuration. I specify which script run config you have to run, which parameters we have to sample, what is the primary metric goal, so that is accuracy. And that is the thing I'm logging here. So that is the metric it has to look at. The goal is that the higher the number is, the better it is. You can make 6 random configurations and you can run maximum of 8 jobs next to each other. So let's submit this job. So this actually works the same as the one before. We say experiment, submit. But what it now is doing, it is creating 6 jobs with all random parameters and then under one run. So now we will have a run which has child runs. You will see for it to spin up, the cluster is doing nothing, so that should be all right. You have the logging. You have to wait like a little bit for it to start up. So we can go here. We can go here to the machine learning environment. Go to experiments. You should see, yeah, here is our hyperparameter drive. It's running. And here we should see all the different child runs coming in. There are no child runs to display because it didn't start up yet. Here we see that it's monitoring for accuracy, and here we will have all the graphs showing in a little while. So it is starting. So now we should be able to follow it also here in our notebook. So our 6 jobs have been queued. You can click on those jobs to have the same experience as in the previous notebook, but then per job. We see it is starting. And soon, so it will not train. Here we can also see which parameters it shows for us. So 3 training rounds, learning rate, momentum, it picked some random values for there. And here we can monitor how it is going. So we have now 2 runs that actually gave us some parameters. So run number 260 is better than 161. More data coming in. Still number run is the winner. It's done 264 as being close. And here we can see it like in a very nice way that if you have 4 training rounds and a low learning rate and a high momentum, that it gives you like a pretty good accuracy. So all the 6 runs are completed. Number 1 is definitely the winner. And there are more types of graphs. You can have like this graph. You can turn it around and see how they all are fun to play with. But the thing I'm interested in is like I need the best model. So I just ask Hyperdrive run, get me the best run by our primary metric. I can register it. I see it here, and then I can register it like Lego Simpsons figures also. Conference here with test 1. Now version 7 is being registered. You can find it back here, and this one under models. Lego Figures is number 7. And from here we can go back again to the run, to the experiment, and to actually the data that is being used and which parameters now has been used to actually generate this model. So I want to close off with like a small recap of what we have done. We first started with setting up our environment, set up compute and storage because we needed that to start training. Then we started experimenting with our data. We created an experiment, trained our model and registered our model. We also tuned our hyperparameters during the training process and registered that model. Then we created the deployment and we actually deployed our model to an Azure container instance so we can use it as an API in the rest of our applications. So all this code is available on ak.ms/Azure Machine Learning AMLS-PyTorch. More things you can find on my blog, Microsoft Learn, Microsoft Docs, but there is a lot of sample code on my GitHub-Henk. So I hope you all enjoyed. And if you have questions, my Twitter is always open to help you get started.
I don't see any further questions in the chat, but really, really interesting. So the code from the charts you show, it's here in this GitHub.
Yes, it is 100% the same. Yeah.
This was awesome, Henk. I really like that Azure Machine Learning Studio offers, let's say, different options for data scientists and also for, let's say, citizen developer data scientists. There is another topic, but that we will explore later, which is the designer. But in this case, also an interesting part is that if we require more compute power, we can just scale our virtual machines, environments, and proceed with it.
Yeah, it has so many features. There is also automated machine learning that will help you choose like the right algorithm. The designer to like what we did now was kind of created our own jobs in our own scripts, but then you can kind of drag and drop them. So there are a lot of cool features in, and we didn't even talk about pipelines to actually bring them in production. So there's so much to talk about. You can fill up all day.
Yes, perfect. Maybe you one question. I saw that you showed the widget to see how the job is doing. If this takes some time, also the performance. Are there any other popular widgets that you might know?
No, I always use this one. It comes
Yes.
with Azure Machine Learning. It is a separate pip package you have to install. But the cool thing is it also works in Visual Studio Code. So if you run your Jupyter Notebook in Visual Studio Code, it will also work.
Perfect. That's really awesome. Any final question, Luis, from you?
Well, maybe we have some minutes to discuss about AutoML. Do you have any experience with that? My experience with AutoML, I tested it with code and with the wizard. And Microsoft, it looks like they want to empower final users to just put a data sets and get predictions, but I think you need some knowledge anyway to understand what you're doing. So you need to understand the metrics, what's the best metric to evaluate. Is not just accuracy all the time. It can be something different. So what do you think about it?
Yeah, so how I see it is that it kind of helps you pick your direction where you want to go. So obviously you need to know what algorithms and how they're doing. I totally agree that if you don't know anything, you should not make any models that go in production and make like life decisions for people. You should be careful anyway with those kind of models. But if you are experienced, you're going to try all these models out manually. It's kind of like the automatic hyperparameter tuning functionality. You have to test out different models and you want to compare them. So for that, automated machine learning is like really handy to like kind of get like a base understanding which model will work on your type of data. I heard people calling it like get like a baseline and start working from there to improve it, to actually try to explain your model and learn from it.
Yeah.
Excellent. Henk, any final words could you share about global AI community? There is a great movement, and you can even invite any people who is watching us, because there are some cool events coming next year.
Yes, it will absolutely be very cool. So the Global AI community is a group of, I think, around 150 to 200 organizers around the world that organize a bootcamp, in this case in July, on the same day. So there can be in person, they can be online. Looks like it's going to be all online. But and that is really to learn with your own local small community. So people will go in a Teams call, do some workshops. Other people will, other events probably will have some local speakers in local languages. So it is not only English, which I find like really cool and really great of the bootcamp. I think you also organized one in Spanish, right? Like last time.
We did last time.
And that really empowers these kind of events for everyone to get into AI and learn actually what it is, what you can do, and that there are a lot of different ways to go in AI. You don't have to be a data scientist to work with AI tooling in your application. We saw it also in the previous presentation about Luis. And those kind of things. These are ready-made APIs, so also developers and everyone can leverage those services. So that event will take place on the 14th and 15th, and we will have the 2 days before. We will have a lot of interviews with all the organizers, and they will get invites pretty soon for that.
Yes.
Yeah, so we will kind of make an overview of what is going on where, and then we will have some Microsoft people talking about some new technology, and then there is also a challenge to get people up and running just before the bootcamp, so they come prepared to the bootcamp and then learn with their local peers.
Excellent. That's a really nice surprise. So looking forward to it. In January, it's the next event. And well, I would like to share that I really enjoy looking at pictures from the previous event, the Global AI Back Together. It was a fitting name, and I enjoy that. Well, you were even in different events. I think in Sweden, also in Belgium, and maybe I'm forgetting something, but it was really nice to see people gathering.
Yeah, it was really nice. That was still the month that we could do it. I don't think it's possible anymore at the moment in the Netherlands, but yeah, we will see what it what it brings. As long as we are all together and can have a chat and talk about AI, I'm happy.
Excellent, excellent. Thank you very much, Henk. We appreciate that you joined us today.
Yes, thank you for having me, and good luck with the rest of your day.
Awesome.
Thank you
Very much. Bye.